And we are streaming online. Yeah, we are live now. So what we can do is we are supposed to solve the problems of linear algebra questions from previous year MHSET examination, and we will be starting with 2015 now. Okay, so slowly I'm just trying to improve myself. What I will be doing is we'll be just reading the question and try to solve the answers. I haven't solved this question prior to this. Will be a fresh question set for me. Let's just read the questions. There are three papers in 2015. It is paper 1, paper 2, and paper 3. Paper 1 is often general mathematics. Paper 2 is most of maths, and paper 3 is most of statistics. Right. So let's just start with this. Question number 5. Let the linear transformation from R3 to R4 be such that my T of 1, T of E2, and T of E3 has been given. Then based on it, what could be this? Okay, so what I observe is my T of this is all of them are 0. That means Z should not be there present anywhere, which is the case. Yes, it is right. Now in the first, X should be only once. Yes, in all of them. In the second, X, Y should be added once. So either of them can be answered. This cannot be the answer. Now the third, is it right? They what they did is T of X would be what then? T of X. How could we generalize this? By the way, yeah, we can generalize it. So that is fine. Now in the third term, there should not be any X. Yeah, we here. I think we just need to use this. In this equation, if I put T of 0, 1, 0, I should get something. So if I put this, then I get 2, 0, 1, and 3. So A cannot be correct. If I just see in this B, in the B, if I put 0, 1, 0, let's see what happens. It should be 2, 0, minus 1, minus 3, and which is something that we require. So option B is the correct one. Right, great. Now the dimension of the vector space sigma square, where x and y are real numbers. Sorry, x and y, the order pair is x comma y. Uh, X and y are the complex number over the field of real numbers. This is a trick, my dear friends. So, my dear friends, if you just try to observe this, uh, what we have complex number over the real numbers. So how we can define the dimensions? If you observe anything over here, what could be the basis? The basis will be 1, 0, I 0, it will be 0, 1, and it will be 0 comma I. So this is going to be the basis, right? This is I. This is going to be the basis for the sigma square, and hence the dimension is 4. So always remember, they always try to play it with you in the sense of complex and real. So it's easy. I think it was option A is correct. Let's go to question number 7. Let's see R with vector space of all continuous real functions over R. Then which of the following set is independent over CR? If you observe the questions carefully, they have given a good set of questions. What they are asking for is linearly independent. So from the book of calculus volume 2, there is a result, a beautiful result, which I still remember. If AIs are distinct, if AIs are distinct, then my this set A AIX is linearly independent. So by using that result, this should be a linearly independent set. So we should not be worried about the rest of the part. Right? Then it is easy, actually. So good question again. Which of the following is a subspace of a vector space C close interval a comma b, set of all continuous function on the interval a comma b? Okay, let's see about this. What we can do is, um, f is an element of C a comma b. F of a is nothing but 1. Okay. So I feel that this first one itself is not a subspace. I need to find someone which is a subspace. Arre Baba, this is definitely a subspace because it will satisfy the condition of alpha W1 plus W2, right? The D will definitely satisfy that condition. So D is a subspace because if I consider any two element from it and take an alpha from the scalars, then F alpha F plus G will again be an element of it. So my dear friends, this is going to be a subspace of C A comma B. If you observe any other, it won't satisfy the condition of the subspace. We know that a W is a subspace of V if and only if this is an element of W for all W1, W2 inside W, and for all alpha inside the scalar field F. So this was a good question. As I always see, the MH set has a simple set of questions, but there should be some different strategy to be applied to clear it. I think slowly I'm going to understand what the strategy is, right? Okay, so let V be an n cross n skew symmetric matrix, okay, over R. That is also important. Then V is a real vector space of dimension. We are just supposed to find the dimension of this V. Actually, I have just noted down it. What was the logic actually is, suppose if I know the diagonal entries, and I know the upper half of this. So by using this upper triangular, I can find out the rest of the stuff, right? So based on that logic, I know what I need to find out, how many elements are there in the upper triangle. So there are n elements in the diagonal, then n minus 1 in the upper triangle, then n minus 2 inside the upper, then the diagonal, and so on till 1. So this is nothing but sum of n elements, first n natural number. So it is nothing but n plus 1 by 2. Option B is correct. If it was q, oh, it is q symmetric. So I just need to find out this part only. I need to find out only this part. This part, the diagonal is already 0. So I don't need to find out this. So this is same as n minus 1 ka sum, yani कि it is n minus 1 into n by 2, and the option A is correct. So this is a silly mistake that we should not have made. So we need to be relaxed while the exam, right? We need to read the stuff carefully. Yes, yeah. Let's come to the next question. Which of the following polynomial is a characteristic polynomial of a matrix which is not invertible? Not invertible, that means the last term must be 0, which is there inside B. If the last term is 0, the last term is always a determinant, right? It is always a determinant. So it could have this different sign, right? Yeah. It can have a different sign. Means what I'm trying to say, my dear friend. The last term always represent determinant, but it could have a different sign based on the order of it, right? So if the constant term is 0, that means that determinant is 0, hence it is not invertible, hence B is the correct choice. Okay, it was an easy question. Let P and X be the vector space of all polynomial of degree at most n with the real coefficient. Then the dimension is nothing but n plus 1. What is the basis, my dear friends? It is 1 x till x raised to n. So this is nothing but n plus 1 dimension. Which of the following is false? Okay, let's see the first statement. Vector space C over C. Wow, this is something interesting. Vector space C over C. Then for the any scalars is this if and only if alpha is equal to 0. Na, ji, na. If you observe, I have alpha 1 plus beta I is equal to 0. If I choose still it satisfies that equation, yaar. हो गया यार, खत्म. It's still satisfying that equation. Hence, this is false. It was so easy. Thank you. The only reason I am able to solve this question simply is because I have read one reference book. This time the strategy is to understand the concept through the reference book and not going towards the notes. Means I have created notes, but I don't say I just want to read the notes. I want to remember the points. वो concept से नहीं जाना. This time I just want to read the reference book as much as I can. Okay, let U and B be the vector space of the dimension M and N respectively. Then dimension of the space homomorphism from B to U, my dear friends, homomorphism is nothing but the linear transformations. So this is nothing but of the dimension M into N, right? It was a good question. Good question. The number of similar classes of 6 cross 6 matrices over C with the minimal polynomial this and the characteristic polynomial this is this is going to be the one of the difficult question, my dear friends, because we need to use a Jordan canonical form, I think so. Similar classes of 6 cross 6 matrices with the minimal polynomial. I think they are just trying to tell us how many uh, classes can we matrices we can form, right? Similar classes, yeah. We need to think about it. So what I know is, if I just think about this in the usual way, it is a 6 cross 6 matrix. What I'm trying to do is I'm just trying to find the Jordan canonical form. Okay, what would be the Jordan canonical form in such case? Okay, so I know it is a 6 cross 6 matrix. And now based on it, what is a block size of 1? The block size of 1 is maximum size 1, and there should and there are two ones, so there should be 1 1. So this is the first block and this is the second block. Now this is 4 and this is 2, so maximum size could be 2. So based on this, what I can do is maximum size could be 2, so I can make this. Or what could I do is I can make one more in this. This is fixed, right? So for the one I have this. How I'm able to write this? By using Jordan canonical form, right? So the other one could be this. So now what is something that we could do in this case is we can make a permutation of them. Nothing else we can do, right? So a number of similar classes of 6 cross 6 matrices over C with this and this. Both will be satisfied, right? Based on this, yeah. Both is satisfied. I think option B is correct, but still, at the end of this, we are going to work on this. Means once I complete this paper, we are trying to work on number of similar classes of matrices. Okay, we'll search this on the internet and see what are the feasible answers possible. Which of the following quadratic form is positive definite? The first of all, we'll try to write positive definite, right? So in this cases, the eigenvalues are 1. In this case, it is 1, minus 1 and 2 are nothing but the eigenvalues, so it cannot be positive definite. In this case, it could be something else. In this case, it is 1, minus 1 and 1. So this also cannot be. So in these two cases, we are just worried of. In the first cases, if I just find out the matrix representation, it is 1 1 1. It is 1 and 1 over here. It is 1 over here, 1 over here, and rest of them are 0. So let us just find out the characteristic polynomial for this. So it is lambda cube, right? It is lambda cube. What are the other things that we can do actually? There are few more ways to think about positive definiteness, but still I'm not going to them because that might be difficult in my head. Let me just go by the simplest possible way at the moment. So it is 3 times lambda square plus a11 a22 lambda minus the determinant. What will be the determinant, my dear friend? What is the determinant of this? Okay, so if I observe the determinant, my determinant over here, my determinant is what? So it is 1 times 1 plus 1, yeah, it is 1 times 0 and minus 1, so it is minus 1, so determinant is 0. Oh, it's done. If the determinant 0, it cannot be positive definite, so the answer C is correct. All right, but for the C, if I just try to why I thought about the determinant, even Sagar, why you thought about it? You can directly see the first and third row are same, hence the determinant should be 0. They are really dependent, buddy, right? Okay, so let's just see this matrix also over here. It is 1 1 1. It should be 0 over here. No. It was nothing but minus 1. What is this? Quadratic form is positive definite. Are they sure about it? This is it is half over here. 0 0 0 minus 1 by 2 and 0. Right? If I just consider this, are the determinant 0? Let me just verify. Actually, if I just multiply this by minus 2, if I just multiply this row by minus 2, what I get is I get no, I cannot get it. I cannot get it. So let me just find out the determinant in this case. Determinant in this case is what? So it is 1 first of all, right? And then minus half times what? Half times plus half. So it is not equal to 0 definitely. So option C is correct. Wow, it was a good question. Now we are just stuck over here in this question number 16. The number of similar classes of 6 cross 6 matrices over C with the minimum and characteristic polynomial this. So we hear that what they meant by this word similar classes of matrices 6 cross 6 matrices. Let us just search that over here. Similar classes of matrices. Two matrices are similar if there exists invertible. What do they mean by it? Yeah, buddy. Yeah, buddy. Actually, buddy, they are just giving me two matrices are similar, and then yeah. Okay, means what? Means what? I got it. I just got what they meant is. In this case, this will represent the similar matrices, right? Because the Jordan canonical form is the same, right? And similar matrices are the same Jordan canonical form, and they may have that, right? So they are just trying to tell you how many Jordan canonical blocks are possible. So from the given data, only two of them are possible. Hence, the B should be the correct choice. Okay. So this was a good session of linear algebra from the 2015 paper. Let us just count it once. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, and 11 questions. It's great. 11 questions. From 2015, there were 11 questions in total, so it is 22 marks. And this inside this, I need to work something, so I'll just continue it later on. But now we can go for 2016 paper. Let's see that paper. In this case, we have keys also. That is advantage. So in 2016, there was a question which is nothing but this. This is going to be one of my favorite questions. 2016 paper I have solved priorly. It has been a time, few weeks I think. But this question was something that troubled me initially. This is going to be beautiful question. First of all, what we know is the concept that we need is we hear what there's a question. T is from R3 to R2, S is from R2 to R3, B to two linear transformation. Then which of the following is true? If you observe the question, there are almost yeah, there are how many options? One, two, three, four. Out of which three are talking about injective. So actually, the question is actually find out whether my S composite T is injective or not. Can it be injective? Let's just think about it. So first of all, I will think about the rank of it. If suppose S composite C, if we try to talk about, it will be from R3 to R3. So if it has to be injective, it should have rank 3, right? So if my S composite T is injective, my dear friend, then it should have the rank 3 since its nullity is identically 0, right? So if it is injective, then my rank of S composite T should be equal to 3. But we know that, my dear friend, my rank of S composite T is less than equal to minimum of rank of S and rank of T. Correct. So it cannot exceed either of them. But in the case of this, if you observe, my rank of S is less than or equal to 2. And the entire answer of this cannot exceed 2. Hence, it cannot be injective. Hence, the answer is done. It was a good question. Why I'm telling it was a good question? Because at the first we think, how could we think about it? But finally, we were able to prove by the simple result. So that is a good point, right? Yeah. So let's just continue with the next result. Next result, question number 6. Okay, so let's just start. Question number 6. W1 and W2 be two subspaces of a finite dimensional vector space, and let dimension of W1 plus W2 is greater than dimension of W. Then what? Okay, they are subspaces, and if addition of the dimension is greater than dimension of W, then it is going to be something serious. Definitely, if the dimension is greater than, they cannot be same as union cannot be same as V. Union is same as V. We cannot think about that. Okay, let me just try to see in some special case. What I do is, suppose if I have V is equal to the plane R3, okay, and then what I see is I consider my W1 as nothing but XY plane, my W2 is nothing but YZ plane, and if I just consider the dimension of W1 plus dimension of W2, then it is nothing but 4, which is greater than 3. So condition is satisfied. Now let's talk about the intersection, since there are 3 conditions on intersection. The intersection is nothing but the y-axis. So is it 0? No. Is it not equal to 0? Yes. Is it empty? No. Is the union equal to V? Yes. In this case, the answer is yes. So what I do, I am just struggling between B and D. So what I can do is, I can consider my W2 same as my W1. Since they are not telling us you need to take this thing, so this is nothing but XY, and still the condition is satisfied. So D cannot be true. It was a simple question, right? Yeah, it was a simple question. Definitely, it was a good question, by the way. So option B is correct. Okay, let's go for the next one. The eigenvalues of real symmetric matrices. My dear friend, we know that Hermitian matrices have real eigenvalues. Eigenvalues, right? And skew Hermitian has eigenvalue either 0 or purely imaginary. Purely imaginary. And my unitary, or what we call as an orthogonal in the real case, has mod of the eigenvalues to be equal to 1. Mod is nothing but the norm of it. right? The norm of it should be equal to 1, the modulus value. So we here need यहाँ पे होना चाहिए था need not be a real number, right? Purely imaginary, need not be a real number, complex number with a unit absolute value. The answer is nothing but this, since it is real symmetric matrix. Okay. Also, there are few more things. All of these matrices are orthogonally diagonalized, right? Yeah, that is a good point to remember. Which of the following statement is false? The product of two orthogonal matrix is orthogonal. It is going to be a beautiful question, by the way. Okay, the product of two orthogonal matrix is orthogonal. I think so. It should be orthogonal. But let me just think about the product of two Hermitian matrices is Hermitian. Inverse of a non-singular Hermitian matrix is Hermitian, the product of two unitary matrix. So I think the point of trouble could be in C or D. Let's just think about the Hermitian first. So let A and B be two Hermitian matrices, right? So they are Hermitian matrices. That means what? That means my A is equal to A star and my B is equal to B star. What I need to prove is the product is Hermitian. That means I need to show that my AB whole star is same as AB. Now let us just think about this AB star. So my AB star is what? My AB star is nothing but AB whole transpose and then conjugate. So it is nothing but B transpose conjugate, A transpose conjugate, that is B star, A star. And that cannot be same as something that you are looking forward to, right? So this could be same as what? It could be same as BA. Nothing else you can write in its place. So the product of two Hermitian matrix is not Hermitian. And my dear friends, you can also verify that rest of the statements are true. If you take a product of two orthogonal matrix, yes, it is an orthogonal matrix. If you take an inverse of an orthogonal matrix, yes, it is, because we have the property that A inverse and transpose could be interchanged. By using that property, you can prove the B also, and the product of two unitary matrix is always a unitary matrix. There is also good result. So C is the correct choice, which is a false statement. Suppose lambda is an eigenvalue of a non-singular square matrix A, then adjoint of A. My dear friend, we hear what they meant by adjoint. This is another adjoint. A star is also called as an adjoint, but we hear this is the adjoint of that determinant wala. Right? So what we know is, we know that A inverse is equal to 1 by determinant of A times adjoint of A. Okay, therefore my determinant of A will be some number into A inverse is nothing but adjoint of A. So what will be the eigenvalues of this? This will be determinant of A times lambda inverse, which is nothing but this, right? Correct. This is the simple properties of eigenvalues that we are using. The dimension of vector space M, where these are nothing but complex number over the field of real number, because they just want to trouble us, nothing else. First of all, if it would have been over C, then it would have the dimension Mn. Since it is over R, I need to separate real part and imaginary part, so it becomes doubles. So it is not Mn, it is 2 times Mn, right? So that is nothing but option B. Let the linear transformation T from R3 to R3 be the given by the reflection with respect to the origin. Then the matrix of T with respect to the standard basis. Okay, with respect to the origin. Okay, reflection with respect to the origin. From this, this is nothing but identity actually. This is nothing but identity. In this case, what will happen is, it is with reflection with respect to something. Yeah, reflection with respect to origin. Reflection with respect to origin. What? How could they think about reflection with respect to origin? Means that will get just reflected in the opposite direction. It will just change its direction, right? So if that is the case, means if I just try to imagine that what they are trying to tell is, suppose if this is the vector, then the reflection is nothing but going like this. With respect to origin, it will just change its direction. Now means the direction is exactly opposite, right? So that is nothing but what they meant. Okay, it's totally fine. I just tried to understand it. But this is identity definitely. In this case, what will happen in the case of B? This will send x, y, z to where it will send it. It will send it to minus y minus x z. Where this will send her as x, y, z will be shared to minus x minus y minus z. And where the last one will be sharing is, it will be sharing x, y, z 2 minus x, y, and z. So if you observe carefully from the given question, I think option C should be correct. Like, what do you guys feel? Uh, I'm alone over here. No issue. Um, no issue about it. So I feel option C is correct. What do you feel, Sagar? With respect to the origin of the matrix of A with respect to the standard basis is क्या लगता है लॉक किया जाए? Hmm. Yes, I feel so. We should lock that question. The answer should be this, but I'm trying to figuring out what they meant by the reflection with respect to origin. Does they actually mean just taking negation of everything? If it is the case, I am right. Yeah, it is right, it is right. If I just want to change everything opposite, then I should change the sign of everything. For an example, suppose if I have the matrix over here, if I suppose I have an element over here, and I want to take a, suppose this is 1 comma 2, and I just want this over here, then how I can obtain is this, I just have to change it in that case. What do you feel, guys? With respect to origin, right? So it is with respect to origin. So it is the same thing with the same that, right? So what should be this? This is what? This is 2 and this is 1, right? Yeah. So how much should be this? How much? Is it minus 1 and 2? Then it would have something else, buddy. It should be 1 and 2. Then if I just observe it like this, no, 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 buddy, no, buddy. What does a reflection by origin mean, yaar? Means they're trying to tell that reflect with respect to this. I think so. I don't know. I'm not. I'm unable to guess it. Reflection with respect to origin. What do they mean by it? If we just search the word reflection with respect to origin, reflection with respect to origin. Reflection in a point when you reflect a point on in the origin, all the coordinates are neglected. Very good. So, ha ha ha. So we were right, my dear friend. If you are taking a reflection with respect to origin, everything will get negated. Hence, the C is correct. Okay. Which of the following matrix is not diagonalizable? The one which, what we'll do is we'll just find out which of them are diagonalizable. Since in this case all the eigenvalues are distinct, it is diagonalizable. We don't know about B at the moment, but if you observe C and D, they are diagonalizable because the eigenvalues are distinct. Hence, B should not be diagonalizable. So it's always happening in the mid-set paper. The question is difficult, then go for the option. It becomes easy, right? Otherwise, it should have been difficult to find out which is not diagonalizable. But from the option, it became easy for us. Okay, now let's come to the paper 3. There will be less questions. Let T1 and T2 be a linear operator or a finite dimensional vector space V over F. Suppose T1 and T2 are similar. Consider the following statements. T1 square, T2 square are similar. So what I can think over here, my dear friends, suppose linear operators, that means I consider them to be a matrix. So suppose T1 corresponding to the matrix A and T2 corresponding to the matrix B. Correct. Now, if I know that my A is similar to B, I want to show that my A square is similar to B square. Okay, so if I know A is similar to B, I know that my A can be written as P B P inverse for some invertible matrix P. So if I just see this is something P B P inverse, P B P inverse. So it is something P B square P inverse. Hence, I know they are also similar. Okay, that was a good question. This is true. What we have to consider the following statement. So one is true, right? From this, we have to choose accordingly. So this statement cannot be right. So what we just try to do is we just try to think about 4. Option 4 over here. These are similar. Okay, what do you feel? Can they be true? None of 1 or 2, 2 is 4. This is also wrong. Only 1 is true. Each of 1, 2, 3 is true. Okay. So only 4 is true is wrong. None of 1 to 4 means 4 is definitely wrong from the options only we got to know. Now we need to think about 2. If 2 is right, then we are done. Correct. So let me just have to think about A inverse. So my A inverse can be written as P B P inverse K inverse. So it is same as what? This is same as actually P B inverse P inverse. So yeah, they are similar. So this is also true and this is also true. Yeah, first, second, third statements are true. Only one is not true. So option D is the correct choice. Yeah, it was a good question, right? You can see sometimes if you are unable to show something, options are good enough to take one of the correct option, right? For the matrix A, the characteristic polynomial is this and the minimal polynomial is this. So the Jordan canonical form, I always get happy when I see Jordan canonical form. The reason is really simple. Initially, I was too scared about Jordan canonical form. But once I understood the concept, how to actually find out, I started getting interested into finding out the Jordan canonical form. So this is definitely not the Jordan canonical form. What is the dimension? Dimension is 6, so it is 1, 2, 3, 4, 5, 6. Right? It should be 6 cross 6. In that also, for 2 there should be 4 entries, so this is fine. This is fine. And for 3 there should be 2 entries. Yes, that is also correct. Okay, so from the given options, if you observe, then the Jordan. Okay, so what I know is from the data, I know it is 6 cross 6. It would be 6 cross 6 matrix. Now, from the characteristic polynomial, I know how many 2 will be there. There are 4 2. 1, 2, 3, 4. Now, maximum size of the block is 2. So, one way is to have 2 blocks, and other way is to have, I know there will be 4 2, right? So, one way is that, and other way is to have this way. Block means this upper diagonal should be 1 then. Now over here what I know is there are 2 times 3, and from the minimal polynomial I know the size of block, maximum size of block present for 3 is nothing but 2, so it should be like this. So it should be like this. So either of them would be the correct choice. And from the options, if you observe, uh, which one is correct? This one is correct. Option C is correct, right? Yes, yes, yes. Option C is the correct choice. So this is a good question. Yep, yep, yep. B, the matrix of orthogonal transformation. I think this is nothing but a reflection. No, it is rotation about z-axis, which is also clockwise direction, right? Inverse of this would be what? It would be reflection around that in the anti-clockwise direction. Correct. So that should have just minus on this place, right? It should be like this. Nothing else. It was simple. Correct. Yeah, it was simple actually. Correct, correct, correct. It is fine. Oh, we are done with the paper. So let's just count the number of questions that we solved, dear friends. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 11. So you can see there are 11 questions to be solved. Okay, so I think tomorrow again I will come with the next 3 papers. So we'll meet tomorrow, guys. Thank you so much, guys, for watching my video. If you are watching, if you're not watching, still it's fine. Whenever you want.